Bismillahirrahmanirrahim. Here is the outline for today's lecture. We'll check what are the second order circuits, and a classical form of second order circuit is a series RLC circuit. For series RLC circuit, we will formulate differential equations and we will check the zero input response of series RLC circuit. The type of zero input response could be either the overdamped response or the critically damped response or the underdamped response. These three types of zero input response for series RLC circuit will be discussed. Towards the end of the lecture, we will have few questions for you to think about and gauge your understanding about what we have covered so far. You will also be provided with the solution of those questions. Let's start with the second order circuits. Second order circuits contain two energy storing elements that cannot be replaced by a single equivalent element. These two elements could be of the same type, like both of those could be capacitors or both of those could be inductors, and this is also possible that one element is inductor and the second element is capacitor. The second order circuit have differential equation that involves the second derivative of the dependent variable. Dependent variable means the state variable. If we have inductor and capacitor in the circuit, and we know that for capacitor we have a state variable which is inductor current, and for capacitor we have a state variable which is capacitor voltage. So we can write the differential equation of a circuit containing inductor and a capacitor in the form of either inductor current or the capacitor voltage. There is an endless number of such circuits. Such circuit means the second order circuits. However, two classical forms which are series RLC circuit and parallel RLC circuit, those would be considered in these lectures. Today we will discuss only the series RLC circuit, and the parallel RLC circuit would be covered in the next lecture. Here we have a series RLC circuit because it contains a resistor represented by RT, Thevenin resistor, and an inductor L in series. All three components, resistor, inductor and capacitor, are connected in series, and here we have a Thevenin voltage source which is represented by Vt of t. So this is a second order circuit because we have two energy storing elements, and these two energy storing element cannot be converted into one energy storing element. Therefore this is a second order circuit. How to write the differential equation of such circuit? We have already checked in our previous lectures that the procedure to write the differential equation involves two steps. First step is to apply the KVL or the KCL equation for that circuit. So here we have a loop, therefore we can apply KVL equation, and the KVL equation in this loop would be Vt of t equal to voltage across resistor is represented by Vr of t, so this is plus Vr of t plus Vl of t plus Vc of t. This is the KVL equation around the loop. Second step is to substitute element constraint equations in above equation. Element constraint equation. What are the element constraint equation? Here we have the element constraint equations for resistor. A resistor voltage Vr of t is equal to current flowing through the resistor multiplied by the resistor value. V is equal to IR formula. So this is the element constraint equation for resistor. For inductor, we have VL of t, inductor voltage, is equal to L di by dt. Or we have an inductor current equation, I of t is representing the current flowing through that inductor. So inductor current I of t can be written as 1 over L integral of VL of x dx, integral limits from 0 to t plus I of 0. I of 0 represents the initial value of inductor current. Similarly, for capacitor, these are known as element constraint equation or the voltage current relationship for these dynamic components as well. So current flowing through that capacitor I of t is equal to C dVc by dt, or the capacitor voltage Vc of t is equal to 1 over c integral of I of x dx, integration limits from 0 to t, plus initial value of capacitor voltage Vc0. These are the element constraint equation. So if we initially focus on this KVL equation, we know that we have three unknown variables. Vr of t is unknown variable, VL of t is unknown variable, and Vc of t is unknown variable. So all these three unknown variables, we basically want to convert them into single unknown variable. And that single unknown variable could be either the inductor current, and inductor current in this circuit is represented by I of t. I of t is the inductor current. It is also the capacitor current and the resistor current, as the three components are connected in series. So we want to convert this KVL equation in the form of one state variable. The two state variable for this circuit are either Vc of t, capacitor voltage, or the inductor current, and inductor current in this circuit is represented by I of t. So we want to convert the above KVL equation in the form of either Vc of t or I of t. Let's try to convert it in the form of capacitor voltage. For Vr of t, we know that the voltage current relationship or the element constraint equation is Vr of t can be written as I of t into R of t, RT. So let's write it I of t into RT plus VL of t. VL of t is inductor voltage. Inductor voltage can be written as L di by dt. L di by dt plus Vc of t. So Vc of t, let's keep it as it is. Now we have two state variables in this equation. One is Vc of t and the second one is I of t. We want to convert this equation in the form of a single unknown variable, either Vc of t or I of t. Let's try to write this equation in the form of Vc of t first. So it means I need to relate the inductor current I of t with Vc of t. For Vc of t, we know that this is the relationship. Capacitor current I of t is equal to C dVc by dt. So it means I can replace this I of t and this I of t with this equation, which is C dVc by dt. So let's write this Vt of t equal to RT, this is constant coefficient, into C dVc by dt plus L derivative of I of t. So when we take the derivative of this equation, it becomes the second derivative. So C constant, second derivative of Vc of t plus Vc of t. So in this equation, RTC, these are the circuit parameters, the value of resistor and the capacitor. These are known parameters. So this is the constant coefficient of the derivative of Vc of t term. LC, this is again the inductor and the capacitor circuit components. Therefore, it is a constant coefficient of the second derivative term. Here we have dt square plus Vc of t. Vc of t is the state variable. So it means we have written the differential equation for the series RLC circuit in the form of capacitor voltage. This is a second order differential term because the highest power of derivative involved over here is power 2. Therefore, this is a second order differential equation of the circuit. RTC and LC, these are the constant coefficient of this equation. As I mentioned earlier, that we can also write, we can convert this equation in the form of either Vc of t or I of t. If we converted this equation in the form of Vc of t, this is the equation that we got. If I want to convert this equation in the form of I of t variable, it means I just need to replace this Vc of t by the current I of t. And we know that Vc of t can be written in the form of I of t using this equation. So this is the same circuit, and we are trying to write the differential equation in the form of second state variable, which is inductor current. In that case, we know that Vr of t, which can be written as I of t into Rt, plus VL of t, which is L derivative of inductor current, plus Vc of t. Vc of t can be written in the form of I of t using this equation. So this equation would be 1 over C integral from 0 to t I of x dx plus Vc0 is equal to Vt of t. This is an integral differential equation because it involves a first derivative term and the first integral term. Therefore, this is an integral differential equation describing a series RLC circuit. Integral differential equation describing a series RLC circuit. It means we can characterize the given RLC circuit using either a second order differential equation in the form of capacitor voltage or in the form of inductor current using an integral differential equation, just like over here. Both of these two equations are describing the series RLC circuit, so both of these two equations can be used, but most of the time we go with the second order differential equation, which characterizes the circuit in the form of capacitor voltage. Next, let's check the zero input response of series RLC circuit. As I mentioned earlier, that the second order differential equation and the integral differential equation, both of these two are the equations describing the series RLC circuit, so we can use either of the two, but it is easier to use the second order differential equation, so we'll be using the differential equation which describes the series RLC circuit in the form of capacitor voltage. This is the same equation, but on the right hand side we had the Thevenin voltage source Vt of t. We have replaced that Thevenin voltage source by 0 over here. Why 0? Because we are calculating the zero input response, and when we calculate the zero input response, we substitute the external input as 0. Now if we focus on this equation, what is this equation? This equation states that the capacitor voltage Vc of t plus derivative of the capacitor voltage multiplied by RTC and the second derivative of the capacitor voltage multiplied by a constant coefficient LC results in 0. If we add these three terms together, the result would be 0. So what would be the function Vc of t which could satisfy this equation? Let's assume if Vc of t is a decaying exponential function, the first derivative of the decaying exponential function would be of something like negative amplitude at t is equal to 0, and then an exponential function e raised to power minus alpha t. And this term would be, second order term would be the positive term. So when we add these three terms up, the result would be 0. Because if we take this thing something similar to e raised to power minus alpha t, this thing would become minus something like minus x into e raised to power minus alpha t, and this thing would become plus y e raised to power minus alpha t. When we add these three things up, the result would be equal to 0. It means the general solution of this type of equation would be Vc of t is equal to an exponential function of the form of k into e raised to power st for t greater than equal to 0. This is the general solution of the second order homogeneous differential equation written over here. In this equation, because this is the general solution, therefore k is unknown and s is unknown. And we need to calculate the values of k and s so that we know the exact solution of the given homogeneous differential equation. In order to calculate the values of k and s, we can substitute this general solution of the second order homogeneous differential equation in this homogeneous differential equation over here. So after substituting, result would be LC second derivative. So second derivative term would be k s square e raised to power st plus RTC, this is the constant coefficient, and derivative of Vc of t. So derivative of this term would be k s e raised to power st plus Vc of t, which is k into e raised to power st equal to 0. From this equation we can take k into e raised to power st common, and the rest of the equation would be LC s square plus RTC s plus 1 equal to 0. If we focus on this equation, it means in order to satisfy this equation, either this thing should be equal to 0 or this factor should be equal to 0. And we know that k into e raised to power st cannot be equal to 0. Why it cannot be equal to 0? Because this is the general solution of the given homogeneous differential equation, and if this general solution becomes equal to 0, it means the inductor and the capacitor, which are the dynamic components of the circuit, those dynamic components are not initially charged. There is no response existing. Vc of t is equal to 0 basically if k into e raised to power st becomes equal to 0. It means k into e raised to power st is not, k into e raised to power st is equal to 0 is not a solution for us. So we can take LC s square plus RTC s plus 1 equal to 0. This equation is commonly known as the characteristic equation of a second order circuit. Characteristic equation. What is a characteristic equation? Characteristic equation is a mathematical expression that describes how the system behaves. This characteristic equation determines the form of the natural response of the circuit. Therefore, we call this equation commonly as the characteristic equation. This characteristic equation, because this involves the second power, like s raised to power 2, here we have s raised to power 1 and here we have s raised to power 0. Therefore, we can say that this equation is a quadratic equation, because quadratic equation can be written in the form of ax square plus bx plus c equal to 0. This is the general form of quadratic equation, and we know that the solution of quadratic equation can be calculated as minus b plus minus under root b square minus 4ac over 2a. And the discriminant of the quadratic equation is basically b square minus 4ac. So based on this characteristic equation, we can calculate the roots of the characteristic equation, and those roots would be LC would be taken as this coefficient A of the quadratic equation. RTC would be taken as the coefficient B of the characteristic equation, and C would be equal to 1. So I can write A equal to LC, B is equal to RTC, and C is equal to 1. So the roots of this characteristic equation would be S is equal to minus RTC plus minus under root B square means RTC square minus 4AC over 2A. When we calculate the roots of this characteristic equation, because this is a quadratic equation, so we get two roots of the characteristic equation. It means two roots, let's call them S1 and S2. These are the roots of characteristic equation. Because our general response was Vc of t is equal to k into e raised to power st, and we got two roots of this characteristic equation. It means our general response Vc of t could be written as Vc of t is equal to k1 e raised to power s1t plus k2 into e raised to power s2t. E raised to power s2t for t greater than equal to 0. Why k1 e raised to power s1t plus k2 e raised to power s2t? Because initially we assumed that our response is of the form of k into e raised to power st, but after calculating the roots of the characteristic equation, we came to know that we have two roots. Therefore, we are going to have Vc of t equal to k1 e raised to power s1t plus k2 e raised to power s2t. Now we have calculated our s1 and s2, but the values of k1 and k2 are unknown. How to calculate the values of k1 and k2? Values of k1 and k2 can be calculated using the initial value of capacitor voltage and inductor current. Let's calculate k1 and k2. This is the general solution of the second order homogeneous linear differential equation, where k1 and k2 are unknown. These two are unknown, and k1 and k2 can be evaluated based on the initial value of capacitor voltage V0 and inductor current I0. How do we calculate? In order to calculate, let's evaluate Vc of t at t is equal to 0. When we evaluate this equation at t is equal to 0, it becomes Vc at 0, which is the initial value of capacitor voltage. We can also write this value as V0. This is equal to k1 e raised to power s1t, as t is inserted as 0, therefore e raised to power 0, 1. So this is k1 plus k2 as it is, e raised to power 0, that would be 1. Therefore we got an equation which is, let's call it equation A. Second equation, because this is the equation for Vc of t. Second equation, or the second value of initial parameter, is initial value of inductor current I0. Therefore, we need to write this equation in the form of IC of t first, and then we can evaluate that equation at t is equal to 0, and we will calculate another equation. Let's calculate Vc of t. Let's calculate the equation for inductor current. Inductor current can be written as, how can we write inductor current? I of t inductor current, because this is a series circuit, and in case of series circuit, inductor current is also the capacitor current. So I of t is inductor current and capacitor current. Both of these two currents are same. So I can take the derivative of this equation, multiply that derivative with c. So write it c, derivative of that equation. So it would be derivative of Vc of t. I'm taking the derivative of above equation and multiplying that equation by c on both sides. So c is multiplied on both sides and derivative is taken on both sides. Derivative on right hand side would be k1 s1 e raised to power s1t plus k2 s2 e raised to power s2t. So this factor on the left hand side is c dvc by dt. This is c dvc by dt, and according to the element constraint equation of capacitor, this is equal to capacitor current, and for a series RLC circuit the capacitor current is also the inductor current, so I can write it as I of t is equal to this equation, c k1 s1 e raised to power s1t plus k2 s2 e raised to power s2t. If we evaluate this equation at t is equal to 0, it would be I of 0, c can be divided on this side, so it would be k1 s1 e raised to power 0 would be 1 plus k2 s2 e raised to power 0 would be 1. So this is our equation B. This equation is in the form of inductor, initial value of inductor current, because we have I of 0 over here. So I of 0 is also represented by I0 like this. So I0 divided by C is equal to K1S plus K2S, and initial value of capacitor voltage Vc of 0, which is also written as V0, this is equal to K1 plus K2. So we can solve these two equations A and B simultaneously, and we can calculate the values of K1 and K2. From equation A, let's calculate the value of K1. So K1 would be equal to V0 minus K2. We can substitute this equation in equation B, and that would be I0 over C is equal to K1. So value of K1 is now V0 minus K2. S1 plus K2 S2. So I0 over C is equal to V0 V0 S1 minus K2 S1 plus K2 S2. So I0 over C, we can calculate the K2 from here. So minus V0 S1 is equal to K2 can be taken common. So this is S2 minus S1. So K2 would be equal to I0 over C minus V0 S1 over S2 minus S1. This is the unknown coefficient K2 calculated in the form of known coefficients. I0 is the initial value of inductor current, C is known, V0 is the initial value of capacitor voltage, S1 and S2 are the roots of the characteristic equation, and we have calculated all these values. Therefore, we have calculated K2 in terms of all known parameters. Next, we can insert this equation in this equation and we can calculate our value of k1. So k1 would be equal to v naught minus k2. So v naught minus I naught over c minus v naught s1 over s2 minus s1. S2 minus S1, so this is minus I naught over C and V naught plus V naught into S1. So V naught S2 minus S1 minus V naught S1. So this is V naught S2 minus V naught S1 and plus V naught S1, these two would be cancelled out. So the simplified equation would be, I'm just going to write the simplified equation, and the simplified equation would be V naught S2 from this part. So V naught S2. So K1 is this equation, K1 is this equation, and here we have the equation for K2. Again, when we substitute the calculated values of K1 and K2 in the general response, we get Vc of t. This is the equation for K1, K1 into e raised to power st plus K2 e raised to power s2t for t greater than equal to 0. So this is the general form of zero input response for series RLC circuit. Now we can calculate that what would be the form of this zero input response if we know that the roots are of a specific type. Let's say the roots are real and unequal roots, or if the roots of the characteristic equation are real and unequal, and third type would be if the roots of the given characteristic equation are complex conjugate roots. We know that for the quadratic equation we can have three types of roots if the discriminant is greater than 0. When the discriminant is greater than 0, because the roots of the characteristic equation can be written as s1 s2 is equal to minus b plus minus under root b square minus 4ac over 2a. This equation is used to calculate the roots of the characteristic equation. When the discriminant is greater than 0, it means this value inside the square root is positive, and when this is positive it means we will have real and unequal roots, because here we have minus b plus something and minus b minus something over 2a. Therefore the roots would be real and unequal roots. And in this case, let's say if the first root is represented by minus alpha 1 and the second root is represented by minus alpha 2, then the form of the general solution of the zero input response of series RLC circuit would be, because in this form we can insert the value of S1 and S2, and then our solution would be minus alpha 2 V naught minus I naught over C. This is minus alpha 2 over alpha 1 plus into e raised to power minus alpha 1 t, and then we have e raised to power minus alpha 2 t over here. If we focus on this equation, what is being represented by this equation? This equation is representing that the overall zero input response is the sum of two exponential functions. One is e raised to power minus alpha 1 t and the second one is e raised to power minus alpha 2 t. These values inside the brackets are representing the value of the exponential function at t is equal to 0. These are the basically constant coefficients. So again, this value inside the bracket is also the constant term, and it is representing value of e raised to power minus alpha 1 t at t is equal to 0. Because we have assumed, or we are discussing this case when the roots are unequal, it means alpha 1 and alpha 2 would be different. So this equation states that the overall response is the sum of two exponential functions. Let's say first exponential function is something similar to this one. This is e raised to power minus alpha 1 t, let's say k1 into e raised to power minus alpha 1 t. It means this term would be representing k1, and I'm calling this factor as k1 basically, because this is constant coefficient. And this value was the value that we calculated for k2. So for second exponential function, let's say this is k2, and the second exponential function, let's say the sketch of the second exponential function is like this. This is 5 times constant for the second function 5 over alpha 2, and this is 5 times constant for the first exponential function 5 over alpha 1. Overall response is the sum of these two. When we add these two responses, what would be the total response? This value would go up and this value would be equal to k1 plus k2. This value would be k1 plus k2, and the overall response would be after this point the response is overlapping with the second exponential function, and before this point the amplitude would be higher than the amplitude of both of these two exponential functions. This type of response is known as overdamped response. Why this is called as overdamped, this would be discussed towards the end of the lecture, but we have to keep it in mind that when the roots are real and unequal, our response type is overdamped, and the function Vc of t for zero input response is similar to k1 e raised to power minus alpha 1 t plus k2 e raised to power minus alpha 2 t, where k1 and k2 are constant coefficient, and these values of constant coefficient can be calculated based on the initial value of inductor current and the capacitor voltage. The next case is case B, when the discriminant is equal to 0, and when the discriminant is 0, roots would be real and equal roots. In this case, let's assume that the two roots s1 is equal to s2 is equal to minus alpha. Then the general form in equation 1 is given above. This is the equation which is the equation 1. This is the general solution of the zero input response of the series RLC circuit. So when we insert these values of s1 and s2 in equation 1, our result is this equation. If we focus on this equation, because the denominator was s2 minus s1, and when the two roots are equal, denominator reduces to 0. Denominator of this term is same, this is 0 as well. But if we focus on the numerator, and this portion is minus alpha v naught minus I naught over c, whereas this term is alpha v naught plus I naught over c. So both of these two terms are exactly same but with opposite sign. It means the numerator, when added up together, the numerator reduces to 0 as well. It means the overall Vc of t in this case becomes equal to 0 over 0. So this 0 over 0 form must be dealt in such a way that why the equation reduces to 0 over 0 form. This is the case when the two roots become equal. We have initially checked, like in case A, we checked that when the two roots are real and unequal, our response is the sum of two exponential functions. But if we keep on if we keep on making the two roots close and close, eventually we reach at a point when the two roots become equal. And when the two roots become equal, our VC of t reduces to 0 over 0 form. So in order to solve this case, let's proceed it in such a way that we assume that the two roots are slightly different, and let's state that s1 is equal to minus alpha, whereas s2 is equal to minus alpha plus x, where x is very very small. When x is very very small, it means they are nearly the same. So Vc of t in this case, when we insert the values of s1 and s2 in equation 1, our equation becomes this equation. And we can write this equation as, we can open this minus alpha plus x and we can multiply this term with v naught. When we multiply it with v naught, we can separate out minus alpha v naught minus I naught over c, and this term which is x v naught, we can write it separately. So it would be x v naught over x into e raised to power minus alpha t. Similarly, this term which is e raised to power minus alpha plus x into t, it can be written as e raised to power minus alpha t into e raised to power xt. Then from these three factors, we can take e raised to power minus alpha t common, because e raised to power minus alpha t is present in all three terms, over here, and over here. So taking e raised to power minus alpha t common, and then we can take alpha v naught plus I naught over c over x common from this term and this term. Therefore, e raised to power minus alpha t taken common reduces this x in the numerator and denominator will be cancelled out. Taking e raised to power minus alpha t common, here we will get v naught only. So v naught over here, and from this term we will, because e raised to power minus alpha t is already taken common, and the rest of the term would be minus alpha v naught plus I naught over c over x. It can be taken common from this term and this term. So our resultant equation would be this one. So in this equation, the 0 over 0 form is basically due to this factor. This factor is 1 minus e raised to power xt over x, because we know that x is very very small. When we insert a limit x approaches to 0, it means this term basically reduces to 0 over 0 form. It means we can apply L'Hopital rule on this term, and it would result into, what is L'Hopital rule? L'Hopital rule is, if limit x approaches to a is inserted in f of x over g of x, and the result is either 0 over 0 or infinity over infinity, means indeterminate form, what we do using L'Hopital rule, we can convert this thing into same limit x approaches to a, but numerator and denominator are converted into f derivative of x divided by g derivative of x. It means if we apply L'Hopital rule on this thing, limit x approaches to 0, 1 minus e raised to power xt over x, because this factor reduces into indeterminate form, 0 over 0 form. Therefore, using L'Hopital rule, we can take the derivative of numerator, and derivative of numerator would be minus t into e raised to power xt, and the derivative of denominator would be 1, and we can apply the same limit x approaches to 0 in it. And when this limit is inserted, our result would be minus t into e raised to power 0, which would be 1. So using L'Hopital rule, we can convert this term after inserting the limit x approaches to 0 into minus t only. Therefore, we can write Vc of t as e raised to power minus alpha t into v naught minus alpha v naught plus I naught over c into minus t only. Minus t would convert this into plus for t greater than equal to 0. This is the response of the series RLC circuit when the two roots of the characteristic equation are real and equal. What is being represented by this equation? This first factor is v naught into e raised to power minus alpha t, where e raised to power minus alpha t is a decaying exponential function and v naught is the value of that exponential function at t is equal to 0. What about the rest of the thing? Oh, this e raised to power minus alpha t was to be multiplied by this factor as well. So we had a missing e raised to power minus alpha t over here. So the complete equation is this one basically. So the second factor is t into e raised to power minus alpha t. T into e raised to power minus alpha t, we know that e raised to power minus alpha t is a decaying exponent and t is a ramp function. So combined together, t into e raised to power minus alpha t is known as damped ramp. And this factor alpha v naught plus I naught over c is representing the value of the decaying exponential function at t is equal to 0. If I sketch the damped ramp, which is the product of a decaying exponential function and a ramp function, the result would be a decaying exponential function. Let's say this is something similar to this one, where here we have 5 over alpha, means 5 time constant, and the value over here is basically equal to this factor. Let's call this factor as k2. So this is k2 and this is the sketch of e raised to power minus alpha t, this term, multiplied by a ramp function. The sketch of a ramp function is something similar to this one. This is a ramp. The product of these two functions is, because at t is equal to 0, the value of this function is 0. Therefore, the two values multiplied together would result in a value equal to 0. And after 5 time constant, because e raised to power minus alpha t reduces to 0, when this is multiplied by the ramp function, the resultant would be 0 as well. So from 5 time constant onward, the value would be 0. And from this point onward, value would be something similar to this one. So this is a damped ramp. Damped ramp is added in a decaying exponential function, which is represented by e raised to power minus alpha t, and the value at t is equal to 0 is v naught. So if I sketch this function e raised to power minus alpha t having value v naught, let's say this is v naught, because the two exponential function have same time constant, it means this is this 5 time constant, and after that the value of this function would be 0. When I add this blue curve and red curve, our result would be starting from this point. Let's sketch it by the green curve. So the green curve would be starting from this point, because we are adding the blue curve and the red curve, and the resultant would be something similar to this curve. This is Vc of t, which is a sum of an exponential function and a damped ramp. Exponential function plus damped ramp. If we compare this graph with the graph of the case A, when the two roots were real and unequal, because in that case the resultant Vc of t was the sum of two exponential functions. Therefore, if we sketch that response and this response on the same graph, it would be something similar to this one. I'm sketching it with a dotted line. So the response in previous case, because that was the sum of two exponential functions, so it was existing on top of it, like slightly above it. So this is this response, dotted response, was known as overdamped response, and the response in case B, when the roots are real and equal roots, this response is known as critically damped response. Why this is critically damped response? Because after this the response would keep on moving downward, and when the response keeps on moving downward, this response would get slightly below the x-axis and it would oscillate around the x-axis. Therefore, that response would be known as underdamped response, and critically damped response is on the boundary between the underdamped and the overdamped response. Therefore, this is known as critically damped response. Another thing to keep it in mind over here is when we need to calculate the response of a series RLC circuit for different cases like underdamped response or overdamped or critically damped response, instead of remembering and using this is exact equation, we can write a simpler equation which would be Vc of t, which is the sum of, because this value is constant, therefore we can represent it k1 because this value is constant v naught, therefore we can represent it by k1 and we can write it as k1 e raised to power minus alpha t plus the constant part can be written as k2 into t e raised to power minus alpha t for t greater than 0. This is a simpler and better equation to remember while calculating the response. When we have calculated our roots and we know that the roots are real and equal roots, then we can insert the values of roots in this equation minus alpha t over here, and then we can calculate k1 and k2 based on the initial values of capacitor voltage and inductor current by evaluating this equation at t is equal to 0 and then calculating the derivative of this equation, multiplying it by c, and then evaluating that equation at t is equal to 0. Let's check the third case. This is the case when the roots are complex conjugate of each other. When the roots are complex conjugate of each other, let's say we are representing our two roots as minus alpha minus j beta and s2 as minus alpha plus j beta, where minus alpha is the real part of the root and beta is representing the imaginary part of the root. When we insert this value of s1 and s2 in equation 1 was the general response of series RLC circuit for zero input case. So when we insert this value of s1 and s2 in equation 1, our result would be this equation. Here this is the value of s2, this is e raised to power s1t, then this is minus s1 and this is the value of s2, and denominator was s2 minus s1, so therefore this is equal to 2j beta. Next we can combine minus alpha and minus I naught over c, minus alpha multiplied by v naught and minus I naught over c, and we can write j beta v naught separately. Similar is the case over here. We can write alpha v naught plus I naught over c and plus j beta v naught separately. E raised to power minus alpha minus j beta can also be written as e raised to power minus alpha t into e raised to power minus j beta t. Similarly, e raised to power minus alpha plus j beta t over here can be written as e raised to power minus alpha t into e raised to power j beta t. Then we can separate out this factor, we can write separately, and then this factor we can write separately. So this is minus alpha v naught plus I naught over c divided by 2j beta multiplied by e raised to power minus alpha t into minus j beta t over here, and the next term would be j beta v naught over 2 j beta, which is written over here, multiplied by e raised to power minus alpha t and e raised to power minus j beta t. Same is the case over here. We can separate out this factor and this factor, and the result is this equation. From this equation, if we focus on this purple factors, this purple factor has this thing common, minus alpha v naught plus I naught over c into e raised to power minus alpha t over 2 j beta. This is common over here and over here. So we can take common, and the rest of the thing we get e raised to power minus j beta t plus e raised to power j beta t over 2j. Similarly, from this factor represented by blue and this factor, we have v naught into e raised to power minus alpha t over 2 common. So we can take v naught into e raised to power minus alpha t common, and the rest of the thing would be e raised to power minus j beta t plus e raised to power j beta t over 2. We know that e raised to power minus j theta plus e raised to power j theta divided by 2j, this is equal to sine of beta t, Euler's identity. Similarly, e raised to power minus j beta t plus e raised to power j beta t over 2, this is equal to cos of beta t according to Euler's identity. So we can replace this thing by sine of beta t, and we can replace this thing by cos of beta t, and our equation would be this one. V of t is equal to constant factor into e raised to power minus alpha t into sine of beta t, and v naught over here into e raised to power minus alpha t into cos of beta t. E raised to power minus alpha t multiplied by a sine function, this is known as damped sine wave. E raised to power minus alpha t into cos of beta t, this is known as damped cosine function. If we try to sketch it, it means a damped sine. This is a sketch of, we know that this is the sketch of a sine wave. This is not sketched according to scale. This is a sine wave, and a damped sine wave is the product of sine wave and a decaying exponential function. Decaying exponential function, let's say this has sine of beta t is multiplied by e raised to power minus alpha t multiplied by this constant factor. Constant factor is representing the value of the exponential function at t is equal to 0. So whatever the value we have for t is equal to 0, let's say this is the value, and this is the sketch of the this is the sketch of exponential function. What would be the result when we multiply an exponential function, exponentially decaying function, with a sinusoidal function? Our result would be, so the result of damped sinusoid would be something similar to this is a damped sine wave, e raised to power minus alpha t multiplied by sine of beta t. Similarly, a damped cosine wave would be something similar to, again this is not sketched according to scale, when we add these two responses up, our resultant response is similar to this black waveform. This is the graph of this v of t, a sum of a damped sine and a damped cosine function. So instead of completely remembering this equation, we can simply write this equation as v of t is equal to K2 e raised to power minus alpha t sine of beta t plus K1 e raised to power minus alpha t cos of beta t for t greater than equal to 0. This is a simpler and easier equation to remember, because we need to remember that the response of a series RLC circuit, when the roots of the characteristic equation are complex roots, our response is a sum of damped sine wave and a damped cosine wave. So we can write it as K1 e raised to power minus alpha t cos of beta t plus K2 e raised to power minus alpha t sine of beta t. Where beta, alpha, both of these two terms are basically frequencies, because e raised to power minus alpha t, the exponential function, like this factor should be a unitless quantity, therefore alpha is a frequency and this is known as Napier's frequency, and beta is also a frequency and this is known as radian frequency. And the roots of the characteristic equation, which are represented by S, they are also known as complex frequency. And this type of response is known as underdamped response, because this response is going negative and then going up, becoming positive, so and so on, oscillating around x-axis. The terms underdamped, overdamped, or critically damped, what is damping? Because all these three responses, underdamped, overdamped, and critically damped, they are decaying with time, and this decay is basically caused by the energy loss in the circuit. So damping means energy loss in the circuit. So overdamped response was, we have already discussed that overdamped response we got when the two roots were real and unequal. Critically damped, which is the boundary between underdamped and overdamped responses, it exists when the two roots are real and equal, and when the roots are complex conjugate of each other, the response is known as underdamped response. There is a question: if R is equal to 50 ohms, L is 1.5 Henry, what value of C will make an RLC series circuit as overdamped, critically damped, and underdamped? You are advised to solve this question yourself and then you can compare your result over here. That's all for today. Thank you very much.